Today we are going to discuss on a design aspect of the blast furnace. So before we discuss how the blast furnace height is designed, we first need to understand why height matter at all. So a blast furnace is essentially a giant counter-current thermochemical reactor. Inside the furnace, two major movement happens simultaneously. First, hot reducing gases, mainly carbon monoxide and hydrogen, move upward from the tuer zone. So these gases carry heat and reducing potential upward through the Bourdon column. So at the same time, the Bourdon material, ore, coke, and flux move downward under the gravity. Now the furnace height determining how effectively these two streams interact. So if the furnace is too short, gases leaves before completing the reduction occurs, heat transfer becomes inefficient, gas utilization drop, and productivity suffers. But when height is optimized, we achieve three major advantages. Better reduction kinetics, this is number one, sufficient residence time, and improved gas utilization that is visible through the top gas analysis. So this is why the furnace height is not just a geometric dimension, it directly controls reaction efficiency and thermal performance. So this naturally leads us to the next question. If increasing height gives so many advantages, then why don't we make the furnace infinitely tall? Say this is a fantastic question. So that trade-off is exactly what we will explore in the next slide, and which is going to be very important for the audience. So coming to our scientific logic of the blast furnace height determination. So now we come to the scientific balancing act behind the blast furnace height design. Increasing furnace height definitely improves reduction efficiency. Why? Because taller furnace provides longer gas solid contact time, better utilization of reducing gases, and a more stable thermal reserve zone. In simple word, the burden gets more time to react with the ascending gases. However, there is a limit. As height increases, the burden column becomes heavier and heavier and more compact also. So gas now faces greater resistance while moving upward. This creates several operational risks: higher pressure drop, gas channeling, burden hanging, and most important is permeability problem. So blast furnace design is always a compromise between the two opposing requirements. So one side maximum reduction efficiency, on other side minimum gas flow resistance. So the best furnace height is the point where these two competing factors are optimally balanced, and this scientific balancing principle becomes even more important when blast furnace capacity increases, which is what we will discuss next. So automatically question arises that why blast furnace height increases with the capacity. So here we compare a traditional low capacity furnace with a modern high capacity blast furnace. Older furnaces were smaller because production requirements were lower. The burden volume was limited, gas generation was lower, and reaction zones were relatively compact. But modern blast furnaces operate at extremely high production rates. So when production increases, three things increases simultaneously, and we must have to remember very well these three factors. First is the burden volume increases, second the gas generation increases, and the reaction zone becomes larger and deeper. Now if we keep the same furnace height while increasing production, the burden will not get enough residence time for the complete reduction. So modern furnaces become both wider and taller. The wider profile helps to maintain the permeability and gas flow. The taller profile provides a sufficient residence time and reaction volume. That is why furnace height grows with the capacity. In other words, higher production demand, larger reaction space, and longer gas solid interaction time. But how do engineers systematically determine the height? That complete design workflow is shown in the next slide, and which is going to be a very important one also. So this slide shows the engineering workflow used for blast furnace height design. The process always starts with a production target. Engineers first determine how much hot metal furnace must produce per day. Next comes productivity selection. This defines how efficiently the furnace should operate in terms of output per cubic meter of working volume. Based on the productivity, the required working volume is calculated. Once volume is known, engineers select the hearth diameter, the hearth size, control liquid handling capacity, and raceway behavior. After that, the H by D ratio, meaning height to diameter ratio, is selected. This is a very important design parameter because it controls gas dynamics, burden descent, pressure drop, and furnace stability. Then engineers determine the effective furnace height required to achieve complete reduction and proper gas utilization. Finally, all zones, throat, stack, belly, Bosch, and hearth are integrated into the final blast furnace geometry. Modern blast furnace philosophy is therefore not simply make it taller. Instead, the philosophy is create an optimized wide and tall furnace that balances productivity, permeability, and thermal efficiency. And this entire discussion can now be summarized into our one final scientific principle. So, what scientific principle is saying of blast furnace height design. So, this final slide brings together the complete scientific logic of the blast furnace height design. Blast furnace height influences almost every major internal phenomena, that is reduction kinetics, heat transfer, gas dynamics, permeability, cohesive zone stability, and pressure drop. That is why blast furnace height is best understood as a thermochemical reactor optimization parameter. So a furnace is not designed simply to look large. Its geometry is scientifically optimized to maximize the reaction efficiency while maintaining stable gas flow and burden movement. At the core of the design philosophy lies one ultimate engineering balance, that is residence time optimization versus gas flow resistance control. So if residence time is too low, reduction become incomplete. If flow resistance become too high, permeability problem and instability begin. So the ideal blast furnace height is the point where chemistry, heat transfer, and fluid flow all operate together in harmony, and that is the real scientific principle behind the modern blast furnace height design.